Hello everybody. Today it's a little high-level math section. We talk about Biot-Savart equation and Maxwell, the relationship. Well, Maxwell theory, electromagnetic theory is complete with Maxwell's 4 equations. Okay. Plus Coulomb's equation. Okay, so this is basically 5 equations, and magnetic things is created artificially in order to make a whole thing symmetric and easy to handle. There's no many textbooks said the Biot-Savart law. It's law, and it's described as if it's independent from Maxwell. It's not. Okay. What Biot-Savart equation is we have Maxwell's equation in a differential form. We take this integral form, and that's what the Biot-Savart equation. And actually this equation is wrong. A lot of textbooks make the same mistake. This is the integral along the current path, one-dimensional integral. So this should be I, not a J. The J here is current density, and this should be I, current. So this person argue why this part is not in there in Biot-Savart equation, and he is arguing Biot-Savart assuming this. Basically, there's no electric flux changing in the field, and he is correct. Biot-Savart equation translated only this portion into integral form. If include this, integral form become much more complicated. So they eliminated this and changed this Maxwell equation to Biot-Savart integral form. Okay. So what kind of case is this? This is like infinitely long wire, or you can approximate as infinite, or like this. But if you have a capacitor like that, then this doesn't work because there is a dt. This term comes in. So you cannot analyze using Biot-Savart integral. Okay. So we have to know the limitation of Biot-Savart equation. It's basically one of Maxwell's equation translated into integral form so that we can do actual calculation. But it's dropped out this part. So the next question is then how do you translate this differential format into integral format? Okay, so we talk about Poisson's equation. Poisson's equation, phi equals rho, and there is another Poisson's equation, vector potential J. Now Poisson's equation let's see, let me see. Oh yeah, you need this one here. What's good about Poisson's equation? The Poisson equation is you can calculate E field by take the gradient phi, right? The same way we can calculate B equals vector potential. Okay, so potential function, if we know the potential function, we can calculate E and B. And Biot-Savart has this equation A in the integral form. How do you get the integral form of the potential? We use this. Suppose you have some charge inside and distance R, you want to know E. So you use one of Maxwell's equation. Divergent D equals rho, right? So you integrate its symmetric form, okay? So E equals 4 pi R square and total Q. You have to add up all the Q, right? And its vector R. This is a unit vector. Unit vector we write this way. R hat, that means this way. If you use this kind of format, this is R, this is a reference point, and this is R prime. So it's become 4 pi O. Don't forget the epsilon, right? R minus R prime square and R minus R prime R. Okay. So in order to give this equation, potential has to be 4 pi Q R square. Right? No. This is not actually, this is just a unit vector. So it's going to be like this because it's a negative gradient. E is negative gradient phi. So the phi should be this form. Okay. So you can guess what is the vector potential for this. Okay. It's going to be integral, and this part you have to know that it's integrate of every, say this is the conductor and total I is running. Every current density contribute to this. So if you take an integral on this area first, it will become I. So A, vector A, R will be 4 pi and I, and the remaining integral is this line integral. And R minus R dot dr. So this is the volume integral. See, there are a lot of details missing here. The volume integral turn into I, j into I, and remaining is line integral. So whatever the line goes through, conductor line, you take an integral along this. Okay? And that's gonna be the total, this. Okay, now since B is curl of A or rotation of A, okay, since we know A, vector potential, you take the curl on this. So what's happened is you get this one. And again, it's confusing. This is volume integral. You change to R integral, and this is gonna be I. Okay, so this is the Biot-Savart equation. So what it is just like where is it? Phi. Oh yeah, out of screen. This is the potential equation for potential phi, and the equation for vector potential this, and this you take the curl. The simplest way to get the B is take the curl and get this one. Okay, so this is the integral form of mu j plus whatever, and this one is eliminated, ignored. Okay, so differential form of Maxwell equation change to integral form, so we can do actual calculation along with this, the I, to compute B at this distance, right, which is, this is R prime and this is R, and this vector is a distance R minus R prime. The location of B we can calculate if you take an integral, and if it's not simple shape, then we can use a computer to calculate the approximate integral, so we can get B. Okay, so it's very convenient. So E is much easier, B is a little more complicated, but it's basically the same thing. Vector potential, scalar potential. This potential function, you just take derivative. For potential scalar, you take a gradient to get the E. Vector potential, you take a curl derivatives, then you get the B. Okay, So that's what the Biot-Savart equation is about. It's nothing special. It's not a new law. It's just a different format of excuse me, Maxwell's equation, and it's make it easier to actually calculate the b out of the configuration of I using integral, rather than try to figure out how to calculate. Okay, so Biot-Savart equation is fine. Let's think this very simple case, right? A and I, and Ampere's law tells you B here is something like 2 pi A I. Okay, so how do you get this? The first method, Biot-Savart equation, you take integral from here to here, negative infinity to positive infinity, because this b has a contribution from every piece of I element along this line. So you have to take an integral, okay, to get this result. This Ampere's simple law. The second method is use this right, and you take a integral in this plane, and this become I, and this integral, remember the equations, Stokes theory, according to Stokes theory, it's going to be b dr, right? And along with this, and this is constant because it's symmetric, so it's going to be 2 pi a b. So b equals 2 pi a I. Okay, so we got this one. So we have multiple ways to calculate this. This kind of symmetric case may be easier to use Maxwell's equation to come up with. The brute force method is this Biot-Savart. You just take an integral from negative infinity to positive infinity, all the contribution from I element on the line to this point, then you get this one, the same result. Okay, that's all for today. If you think this video is good, please subscribe and give me a like. Thank you.